Hello there, welcome to the June 2019 paper. Here we're looking at question 4. The infinite series C and S are defined by these two expressions above here. Given that C and S are both convergent, show that C plus IS is equal to this expression here. Okay, well let's write out first of all what C plus IS is equal to, and let's just do it in the columns. So it's going to be cos theta plus I sine theta. Okay, that's a good part there. The next part is going to be a half on both of the second terms here, brackets cos 5 theta plus I sine 5 theta, plus a quarter, cos 9 theta plus I sine 9 theta, and then the last one is going to be plus 1/8 of cos 13 theta plus I sine 13 theta. Okay, that's all our terms added together there. Now let's write each of these different four complex numbers. Now if over this will go plus into exponential form. So it's going to be e to the I theta plus a half e to the 5 theta I plus a quarter e to the 9 theta I plus 1/8 e to the 13 theta I, and then this will carry on plus . Now what we've got ourselves here is a geometric sequence. It's going to go A plus AR plus AR squared plus AR cubed. Now A is effectively going to be the starting term here, so in fact let's just write this down. This is a geometric sequence. This is a geometric series because we're adding it together, where A is the first term, that's e to the theta I, and then R is the thing we're going to multiply from one term to the next, and it should be a common ratio between the terms. So we're definitely halving all of the next terms, and then we're adding on 4 theta onto the onto the exponential. So that's actually going to be multiplying by e to the 4 theta I, because that will then add onto the indice when you multiply with a indice of the same base. So this is an infinite series as well, so we're going to be using the formula a over 1 minus r, so therefore it's going to be e to the theta I over 1 minus a half e to the 4 theta I. Now the final thing we need to do to make it into this thing we want to show is just times top and bottom by 2, times top by 2, times bottom by 2. It keeps the fraction equivalent, so it's going to be 2e to the theta I over 2 minus e to the 4 theta I. And there we are, that's the answer to what we want to show. So we've shown that C plus IS is equal to this expression here. Now moving on to the next bit. The next bit's quite tricky, hence show that S is equal to this expression here. Okay, so just a reminder of what S was equal to. S was equal to all those signs added together. So it's just going to equal the imaginary part of this expression here. So therefore S is equal to the imaginary part of 2e to the theta I over 2 minus e to the 4 theta I. So that's what S is equal to, but let's simplify this expression here first, or not simplify it, but expand it in terms of sine and cos. So 2e to the theta I over 2 minus e to the 4 theta I is equal to 2 cos theta plus 2I sine theta over 2 minus cos 4 theta minus I sine 4 theta. Now what I'm going to do next is to rationalize the denominator and be able to split up the S and the I, C and the I and S into separate parts. We need to rationalize the denominator, or effectively get rid of the 0 on this denominator here. If you think about it, if we had 3 over 2 plus 5i, then the way we would get rid of the I on the denominator is to times by the complex conjugate of the denominator, so times top and bottom by 2 minus 5i. This is effectively what we're now going to do in this question here, but with something much more complicated. First of all, what I'm going to do is I'm going to leave the top alone, and then I'm going to group together on the bottom the real and imaginary parts. So this is the real part, 2 minus cos 4 theta, and the imaginary part is minus I sine 4 theta. So now we need to multiply by the complex conjugate on the top and bottom of the denominator. So it's going to be 2 minus cos 4 theta, and now it's a minus here, so it now needs to be a plus I sine theta. And the denominator, it's going to be the same, 2 minus cos 4 theta plus I sine theta. Now this will get rid of the i's on the bottom of our fractions. But first we need to multiply the top together, so the first bit is going to be 2 cos times 2, so that's going to be 4 cos theta. Then it's going to be minus 2 cos theta cos 4 theta. The next bit's going to be plus 2i cos theta. Oh, sorry, there's meant to be a 4 there, and 4 there. 2i cos theta sine 4 theta. The next bit is with this 2i sine theta, so plus 4i sine theta. And the next bit's going to be minus 2i sine theta cos 4 theta. And the last bit is going to be double negative because, well, no, not double negative, but double I. So that's going to make it minus, so minus 2 sine theta sine 4 theta. And that's all going to be over. Now, when you're doing the times in by the complex conjugate, it's effectively the difference of two squares. So because we'll have a plus and a minus of, so we only need to multiply the first bit by the first bit. If we multiply the first bit by the last bit, that will cancel out by the last bit times the first bit. So we also need to just multiply the last bit by the last bit. So it's going to be 4 minus 4 cos 4 theta plus cos squared 4 theta. Any multiplication of the 2 minus cos 4 theta and the I sine will cancel out with this minus I sine and the 2 minus cos 4 theta. So then it's just going to be minus I times plus I. That'll make it plus sine squared 4 theta. Right, so now this is what's equal to this at the moment. So now I'm just going to take forward the imaginary parts of this expression at the top here. So just taking forward the imaginary parts, that bit there is real, that bit there is real, this bit here is imaginary, so it's 2 cos theta sine 4 theta. I've dropped the I. The next bit is plus 4 sine theta. The next imaginary bit is minus 2 sine cos 4 theta. And the next bit is real, so we can ignore that bit. And then it's all going to be over 4, but then we've got this cos squared 4 theta plus sine squared 4 theta. It doesn't matter what the angle is actually. Cos squared plus sine squared, it will always equal 1. So it's 5 minus 4 cos 4 theta. Great, we've perfectly got the denominator now. Now we just need to sort out the numerator. The numerator already has 4 sine theta in it, so it should be the case that these two bits here and here simplify to this expression at the top here. Well, the 2's are in the right place, so that's fine. And now what I'm going to recall is the sine angle addition formulae. Sine A minus B is equal to sine A cos B minus cos A sine B. Okay, let's see if we can use that here. If we set a equal to, which way would it be best round to do it? If we set a equal to 4 theta and b equal to theta, then this is going to be 4 theta minus theta. So it's going to be sine 4 theta minus theta. And this is going to equal sine theta, so sine 4 theta. So that's a, isn't it? Yeah. Cos theta minus cos 4 theta sine theta. And that does make sense because we've at the back here, I've dropped the sine theta. Because at the back there we've got cos 4 theta and it's on the minus, so this all perfectly lines up with equaling sine 3 theta, 4 theta minus theta, remember. If we do this calculation inside the bracket here, that's going to equal 3 theta. So then this is perfectly 2 sine 3 theta plus 4 sine theta over 5 minus 4 cos 4 theta. And there we are. Oof, lots of algebraic manipulation there, but we got there. We finally found an expression for S. If you were finding an expression for C, you would just take the real part of this big fraction here, but that was the key part to it, creating this big fraction, then just taking the imaginary parts from it, because S here is clearly just the imaginary part of that big long expression there. So there we are. That's all we have to go through for question 4, with 8 marks in total there. Let's now move on to question 5.